Good morning, students. Today we can discuss law of conservation of linear momentum. Law of conservation of linear momentum is not given as a concept in your material, but when it comes for the worksheet, there are some questions related with the law of conservation of linear momentum. And in order to understand the Newton's third law in a better way, the law of conservation of linear momentum will help us. So there is a real connection between the third law and the law of conservation of linear momentum, just like the first law and the law of inertia. Both are same, telling in a different manner. In here also, the concept is actually same, but explaining it in different manner. So here, first we are looking at the statement. Law of conservation of linear momentum. Law of conservation of linear momentum states that momentum of an isolated system is conserved. The word conservation meaning it is something that is preserved, that is something that is kept constant. So no changes occurring to that particular thing. So momentum is conserved. Momentum will be constant for an isolated system. That is the meaning. Momentum will be constant for an isolated system. Now we have to understand what is isolated system. The word isolation is nothing but keeping, for example, during this corona time we may hear the word many times. So keeping something away from some other things. For example, if you are keeping a person away from the community, then that person is actually isolated. In physics, what would be the meaning of isolation? If a system, meaning for example, there are two bodies, A and B. So these two bodies we can togetherly taken as a system. So when we are taking this as a system, A and B, then the remaining of the world is actually surroundings. That is related with chemistry also. So whatever we are giving focus or attention to a single body or a number of bodies. Here we are taking two bodies as a system. So we are considering if this is in order to become an isolated system for both A and B, in order to become isolated system for A and B, or in order to consider this as an isolated system, the only thing is no external force should be acted. No. So F net external force should be 0. If no external force is acted on a system, then those system is called isolated system. So meaning that if net external force is 0, such a system is isolated system. Now you understood. I hope you understood what is isolated system, and now again we are connecting the terms. Momentum of an isolated system is conserved. If net external force on a system is 0, then momentum of that system will be conserved or will be constant. That is the meaning. If net external force on a system is 0, then momentum of the system is constant. That is the meaning of the statement. So the same statement, you can law of conservation, you can state in these words or you can state in these words. That's not a problem. Both are same meaning. When F net external force is 0, if net external force is 0, P is equal to constant. What is P? P is nothing but a momentum. So whenever F net external force on a system is 0, we will be getting momentum as constant or momentum is conserved. Momentum is conserved when net external force is 0. Now imagine the same way. We are having two bodies A and B. Okay. No external force is acted on it. The net external force is 0 on both A and B. If A and B exerts any force each other, then both are moving with certain velocities. For example, A moves with v1 velocity and B moves with v2 velocity. Then A and B are collided each other. After the collision, will the momentum before collision will be equal to momentum after collision? Whether any external force is acted on A and B, if A and B are collided each other. If you are taking A and B as a system, even if A and B are collided, that is not an external force. We can say that is not an external force, since we have taken this as a single unit. A and B taken as a single unit. So even if the A and B exert force on each other, that is not an external force. In that time, it is not an external force. So if external force is 0, the momentum has to be conserved. So even if the A and B are collided each other, the momentum, the total momentum before collision of A and B will be equal to total momentum after collision between A and B, since net external force acting on A and B is 0. Understand the wordings? If A and B are two, if A and B are if A and B are two bodies considered to be a system, even if A and B are collided each other, it cannot be taken as a external force. So unless external force is acted either on A or on B or both, the momentum of the system, momentum of A plus momentum of B is constant even if it collided each other. Okay, so we are considering two bodies of mass m1 and m2. Here m1 is moving with velocity u1 and m2 is moving with velocity u2 in a straight line, and u1 is greater than u2. The velocity of m1 is greater than velocity of m2, so it is moving faster than u2. So since they are in a straight line, since u is greater than u2, after a time m1 will collide with m2. Now we are considering the net force, the net external force acting on m1 and m2 is 0. So the total momentum before collision should be equal to total momentum after collision. Here we are considering the collision. So m1 here, what is the momentum of m1? m1 u1, that is the momentum of mass m1, and momentum of mass m2 is m2 into u2, that is the momentum of the second body. If you are considering this as the first body, the momentum of this body is m1 u1, momentum of this body is m2 u2. Momentum is mass into velocity, product of mass and velocity. So m1 u1, the total momentum m1 u1 plus m2 u2, that is a total momentum. So from law of conservation of momentum, total momentum before collision should be equal to total momentum after collision. So m1 u1 plus m2 u2 will be equal to, after collision we are assuming that the velocity of m1 changes to v1 and velocity of m2 changes to v2. So the total momentum after collision is m1 v1 plus m2 v2. So here m1 u1 plus m2 u2 should be equal to m1 v1 plus m2 u2. Sorry, m2 v2. See, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Total momentum before collision is equal to total momentum after collision according to law of conservation of momentum. Now we have to discuss the relationship between the third law and the law of conservation of momentum, and I will not give any mathematical expression, mathematical relationship, since it is not since it is beyond your scope of study. So consider a balloon. We inflated the balloon by blowing the air into the balloon. So the balloon is inflated, and we are now going to release the, so I am holding the balloon in this hand, and the orifice of the balloon is here. I put it like this. Now I am going to release the orifice of the balloon, so that what will happen, the air will move in this direction, okay. And at the same instant, when I am releasing the orifice, I am releasing the balloon also. So the air will move in this direction, whereas the balloon will move in this direction, isn't it? So now consider air and the balloon. While the air is coming out of the balloon, the air exerts force on the balloon. So the force exerted by air on the balloon, it will be in this direction, backward direction, whereas the force exerted by the balloon on the air will be in forward direction. So that is an action reaction pair, okay. The force exerted by air on the balloon is backward direction. Force exerted by the balloon on the air is in forward direction. That is the action reaction pair here. Now consider this as a system, both air and balloon as a system. Now net force is acting on the system, even though force exerted between air and balloon, it is just a system, so no external force is acted, so the momentum has to be conserved. Now before the release of air, before the release of the orifice, both balloon and the air were at rest, okay. When I release the orifice as well as the balloon, the air moves forward. So we are considering there is a certain mass for that particular air. So that mass into velocity of the air, velocity of the air which comes out from the orifice. So that air having momentum. Before release, air was at rest. So the momentum of the air is 0. Before the release of the balloon was also at rest. So the momentum of the balloon also in that point of time it was 0. So the total momentum before the release is 0 plus 0. For air the momentum is 0. For balloon also the momentum is 0. So the total momentum before release is 0. Now then in order to conserve the momentum, the total momentum after the release should be also 0. So here momentum is a vector quantity. So when air moves in this direction, it goes to some, if you are considering this as a positive direction, the air got some positive momentum, some positive quantity we have to consider this as, if we are considering this as the positive direction, here the flowing air or the air which moves out of the balloon having some momentum. So in order to cancel out, we have to get the same momentum in this opposite direction. So that's why the balloon is moving backward. So that if you are adding the momentum of the flowing air plus momentum of the balloon which are in opposite direction, if you are adding these two quantities, we will get again 0. For example, if it is 5 kilogram meter per second, then it will also be minus 5 kilogram meter per second, since it is in opposite direction. If we are taking this as positive, this should be taken as negative. So if we are adding it, if we we are adding it, we will get again the total momentum as 0. So the total momentum of an isolated system is conserved, and you can see the third law here, and you can also see the conservation of momentum. So conservation of momentum and third law or Newton's third law are the same, just like Newton's first law and the law of inertia. So there are few examples I have to explain. Those examples will be explained in the next class. Thank you.